Hi everyone, welcome to an nTop live video. My name is Julio Aira IV. I am a product design engineering intern at DiveDesign. I am also a student at Penn State University. I'm studying mechanical and biomedical engineering. Today we're going to be talking to you guys about how we use field-driven design for small-scale animal prosthetics. We're also going to show you how we optimize them for SLA printing. So let's jump right into it. So our first model that we're showing here is a prosthetic socket that we created externally in Mesh Mixer. So we used a 3D scan of a duck named Angel to create a socket, right? So as this model stands right here, there's a lot of areas where a lot of material that might be going to waste where we don't really need it. So we want to use fields and lattices to kind of optimize our material usage and optimize for SLA printing, right? So the first step we did was take that imported mesh file and create a remeshed surface, right? So our original mesh file was very complicated. As you can see, there's a lot of detail that we might not need right now, that we want to just kind of simplify for our lattice. So we kept the edge length to 5 millimeters. We used the triangular shape for our mesh file, and this is really what's gonna be the driver in the overall lattice shape, right? So with this remeshed surface, we were then able to take it to a volume mesh, and this is where we can start to use our fields and our scalar fields to drive that lattice. So just as a side note, in nTopology, whenever you see this symbol right here, this means scalar fields. So in nTopology, when a scalar field, you can think of it as a collection of data points that can be a driver for an input, right? So if you think about it, if you take it back to a basic physics class, it was told scalar fields versus vector fields, right? So a vector is something with a magnitude and direction, whereas a scalar just has a magnitude. So it's basically the same idea here. nTopology is a math based software, so it's going to use a lot of those concepts you learned back in your early years of school, at least for me in engineering school, right? So with that being said, we can kind of show you how we use the ramp block and scalar fields. So we created a scalar field list, right, to kind of introduce new collection of data points, or in our case we used two spheres to kind of be where we want to localize those the edge length to be driven by, right? So as you can see, we have two spheres, different sizes of radiuses, so we can kind of use those as inputs for our edge length and to drive how our volume mesh is going to be created. So using that volume mesh, I'm going to skip over the implicit body because we're not going to use it right now, but we were able to create a lattice from volume mesh, right? So this is going to be really unique geometry, whereas in any other CAD software that I've used, it would be almost nearly impossible to create something like this, right? And for those of you that know surface modeling, it's be very difficult to replicate something like this. So as you can see, we have something that's really interesting, and you will notice that near the edges of this geometry, where we kind of reduce the feature size, the lattice does seem to get a little bit more complex, right? And that's really what we want to, right? At the edges is really where there's going to be those high stress points, and any corners, any sharp edges, those are really going to be our stress concentration. So using that volume mesh is really going to help us out in terms of how we can add rigidity and texture to the overall lattice. So going from there, we can use the thicken lattice block, where it just takes our lattice that we created before as the input, and then we're going to create just a uniform thickness overall to create something that is ready to print. So as you can see, we used a uniform thickness, and you will notice that this is a scalar field input, so we will be able to, if we wanted to, drive the thickness of the overall socket in any direction, or using a point or a plane, which we'll get on. We'll get to that later on. So for our next way of creating a volume lattice, we can also use the Voronoi volume lattice. And as you can see, it's very dense, and it uses random points in a body to kind of create that unique looking Voronoi structure. We're not using scalar fields in this iteration right now, but I just wanted to show that there are more than one way to use volume meshes to create lattices, right? So we can use the lattice from volume mesh, and we can use the Voronoi volume mesh too as well. So moving forward, we can look to our next patient, which is a duck named Belle, right? So again, we have an imported mesh file, and we want to optimize that for SLA printing, which means we want to decrease the surface area in between those layers when we bring it into our slicing software, right? So again, this was created using a 3D scan of Belle's limb, and we kind of added some notches in the design, and also a scan of Belle's healthy limb to kind of balance the overall aesthetics of the design. So my opinion, looks awesome the way this came out. So just to bump it up, we want to use lattices and scalar fields to kind of drive where we want the rigidity to come into play. So to do that, we're going to again first remesh the surface, right? So we're going to kind of customize how we want that surface to look, right? So at a first glance, you'll start to notice too, there are areas where the remesh surface is a little more dense than others. So if you can tell, there's areas where we wanted to kind of add a little bit more rigidity to the surface, and we did that using a ramp and scalar field modifier. So again, once we see this scalar field symbol, we know that we can drive it with fields, right? So to kind of go through this, I'll take you step by step. So the first thing we did was create a ramp feature. So what that means is that it's trying to create a kind of gradual transition based on the scalar field, right? So we have an input min, input max, and then an out min and out max, right? So that's going to be the values that we want to use for, in certain areas of the model, right? So for the scalar field itself in that ramp, we're going to use an edge length modifier, and all that means is that we used a scalar field list and several spheres, similar to like how we did before, to kind of localize that surface edge length for our model. So as you can see, with these spheres and the change in radius, we're able to drive where we think the surface lattice should be thicker or more structurally sound. So we added it toward these high stress regions, and if we ever wanted to just come back and kind of play around with the surface based on feedback, it's very easy. All you would do is play around with these center points and even radiuses. And so let's say the patient comes in and tells us, hey, the Belle looks like it's not very comfortable, and it's too rigid right now. We want a more like compliant response, right? So we would probably add or take away certain any of these scalar fields to kind of relax the overall volume or surface mesh. So with this remesh surface, we were able to take a surface lattice and create and what I think is an awesome looking starting point for our lattice, right? So we get all these localized lattices where there is a variable density and edge length in the overall surface lattice. So this is really cool, right? Because in any other software, any other external software, it would be pretty hard to replicate this this model. So really thankful to nTop that we can quickly iterate and use feedback from patients to kind of iterate and remodel all these surfaces. So from there, we just used a thickened lattice, and we're able to get something that's close to ready to be sent for SLA printing. So our second iteration for Belle's foot is going to be using a Voronoi boundary lattice. So for the Voronoi boundary lattice, we used a volume mesh and also the random points in the body for the using the surface mesh that we imported earlier and also remeshed. So again, I'm going to use this boundary lattice, and it's going to create something that's not as dense as the volume lattice. And this application or this block might be used when we want something that's a little bit more compliant, a little bit easier to breathe with, might be easier to clean, depending on how or what feedback we get. We can kind of use this this lattice to kind of create the prosthetic, right? So as you can see, there's a lot more space and a lot more randomness going on in this one, and that really comes from the point count, the relaxed iterations, and the random seed. So as you may have noticed in this block, in the random points in the volume mesh, there is a spatial weighting. There is a spatial weighting input as shown here is the scalar field, which means we can use scalar fields to kind of drive how the weighting is going to be of this overall boundary lattice, right? So this means it can be any form of implicit body, it can be a plane from normal, it can be a point, it can be a plane. So in our case, we used a point in space, right? So to kind of show you where that point is, I'm gonna turn it on. It's very small and it might be hard to notice, but it's at the front port of the prosthetic. So yeah, so we can use points in our scalar fields to kind of drive where we want the spatial weighting to be adjusted, right? So just for a demonstration, I added one, but if we get feedback from a patient saying, hey, we want a specific area of the socket to behave differently, we can use a series of these points and kind of drive how the prosthetic is going to behave with this feature, right? So again, we used a ramp to kind of modify the transition of how the socket is going to act in this region. And as you can see, there's a small kind of transition where the boundary goes from dense to a little less dense, and then we did that using the ramp and the ramp and point in space. So lastly, we want to add some thickness to this lattice, right? Because as it is right now, it's not too thin for SLA printing, so we want to use the thickened lattice, but this time we're not going to provide a uniform thickness. We want the base of the prosthetic to be a little bit more rigid than the rest of the body, right? And that's really where that loading is going to occur towards the base of the foot, right? So to do that, we use the thickened lattice, and since the thickness can have a scalar field as an input, we use a plane from normal to kind of drive how we want the thickness of the foot to change, right? So this plane is gonna start towards the center of the foot, of the leg, and kind of transition from a thinner, kind of maybe a little softer lattice to a thicker and more rigid lattice, right? So this could be, in the future, we could change this to be dependent on a duck's weight. We can kind of optimize how we want to use this the ramp depending on the feedback we get from our patient, right? So it really gives us a lot of flexibility in terms of how we can use scalar fields to drive the overall geometry of our parts. So moving forward, we have a dog prosthetic. So I'm going to run you guys through the workflow and how we get to something like this. So starting off, we want to show the difference between our previous dog foot versus our new foot, right? So on the right here, we have the original foot. This is meant for FDM printing, so it needs to be a little larger and not as complex, right? Because FDM can't handle like the resolution and design requirements that SLA can. So since we have a smaller dog and we want to use SLA printing, we created a base file in SolidWorks that we will be able to modify using scalar fields and field-driven design, right? So the first thing I did is kind of separate these two into implicit bodies, and the main reason is because since this is coming in contact, this portion is coming in contact with a pylon, it still needs to be very dense and rigid, so we don't want to necessarily add lattice to this section, right? So now the first iteration is going to come from a TPMS spherical structure. So as you can see, this model would not be ideal for FDM printing. There's a lot of overhangs and a lot of structures that are not supported, right? So this would be ideal for something that can handle this resolution and this changing wall thickness, right? So to kind of get this geometry, we played around with the longitude count and the latitude count until there's something that we liked, and then as you can see, since the approximate thickness is a scalar field, we were able to add a thickness modifier towards the center of the model, right? So as you can see, the thickness is pretty thick here, and it kind of gradually decreases as it gets to the bottom of the foot. And to do this, we used a point at the center of the model, and that's really how I don't know if you guys can tell, but this is really how we're gonna drive that ramp and that scalar field. So just to show how this thickness is kind of increasing and transitioning, you can use a cross-section view to kind of show how the thickness is kind of changing from the middle outward. So that's really the goal for this model. We want to match the gait of a dog's foot, so we really want something that kind of conforms to that gait cycle with this model. And so our last iteration for our dog foot is going to be using a lattice from volume mesh, right? So for this model, we wanted to create this into a mesh file, right? So similar to our duck prosthetics, we're going to create a mesh from CAD body, then we're going to remesh the surface, and we're going to play with some of those scalar field inputs, right? So similar to before, we used the edge length, and we're using a ramp feature and a plane to kind of drive how that mesh file is going to change from the top of the foot to the bottom of the foot, right? So this region might be where we want a little bit more rigidity for the dog, and the bottom portion we want it to be a little more compliant. We want some compression happening, so we'll play with that ramp to kind of give us a nice smooth transition. So after we remesh the surface, we can also modify the surface and convert it to a volume mesh, right? So we use the volume mesh, and here we have something that is similar to what we had before, that will allow us to use the lattice from volume mesh. So we have something amazing looking lattices that were driven by fields and scalars for our model. So lastly, we provided a uniform thickness to the model, and all we did next was used a Boolean union, and we were able to union that pylon insert and bottom foot for the model. So thank you everyone for listening on this nTop live video. If you have any questions, please feel free to reach out. We're continuing to do more and more animal prosthetics every day. So thank you for nTopology for giving this opportunity.